Welcome to part two from our lecture series from Friday, March 10th, where we just came from discussing like a general definition of molecular orbital theory. We contrasted that against what we know from valence bond theory, and we came to the conclusion that a molecular orbital is formed by combinations of all atomic orbitals on each atom that are involved in a chemical bonding system or in a molecule. So we're now introducing combinations of not just like hybridization of our valence orbitals, but combinations of core and valence orbitals between two atoms. Now, those combinations are what we know as linear combinations. So I've made a statement here, which is summarizing kind of what we left off on in our last video, which states that molecular orbitals are formed by linear combinations of atomic orbitals, which I'm going to hereby refer to as the acronym LCAO, specifically linear combinations of atomic orbitals that have the same principal quantum number. So if we go back up here, we would look at a combination of a 1s from one atom with a 1s on another atom, and then the combination resulting from the 2s from one atom interacting with a 2s of another, etc., etc. Now, why am I using this phrase linear combination? Like, why complicate the language any further than it has to be? That's because a linear combination has some specific meaning. So we need to recall that orbitals, their shape, right, their description, inherently come from some manipulation or mathematical treatment of our wave function. And our wave function is a literal function that describes some kind of wiggly wave, where that wiggly wave is what we are using to model the wave-like properties and nature of an electron. So since our orbitals come from this wave-like understanding of our electron, then their combinations need to be ones that align with how waves combine or interfere with one another. So their combinations, orbital combinations, are reflections of wave interference. So if we remember wave interference, we had kind of two different distinct ways in which we could make waves interfere with one another. We had constructive interference, where our amplitude of our resultant wave was increased as a result of our waves being in phase with one another, meaning that for every peak there was a peak and for every valley there was a valley. So this will generate something like this. This is our constructive interference. And this constructive interference can be thought of as addition. This is like the sum of two waves. We also had kind of the anti interference, meaning like a destructive interference. So this is where we had waves that were completely out of phase with one another. Meaning that for every peak of one wave, there was a corresponding valley on another. And those peaks and valleys would net cancel one another out. So if I were to add these together, this would give me a wave with zero amplitude. This is our destructive interference. And this could be thought of as the subtraction combination. in the sense that here I know that we're looking at an addition, but we're adding a wave that is the anti or opposite or inverse of another. So it's kind of almost like subtracting a negative gives us an addition, where the negative that we're subtracting here is the inverted or -1 version of our original wave. So in order to look at these LCAOs, or linear combinations of atomic orbitals, we need to look at both constructive and destructive interference of those orbitals. So we're looking at both an additive and a subtractive interaction between s orbitals and p orbitals. So let's look first at the formation of our sigma sub s molecular orbitals. So as you might be able to imagine, sigma sub s molecular orbitals result from the head-on linear combinations of atomic orbitals, specifically linear combinations of s atomic orbitals. So this idea of having a, before I use those colors, having a sigma resulting orbital, that's from the head-on combination idea that we saw in valence bond theory. And because we are looking at a head-on combination of s atomic orbitals, the resulting MO is called the sigma sub s. So let's look at what these molecular orbitals could look like. Okay, so here I have a depiction of the two different atomic orbital combinations that could result from s orbitals being combined. Notice here we have the subtraction and the addition. So the addition is our constructive, and this is ultimately something that is stabilizing. And we're looking also at the subtractive or the destructive, which is less stable. In fact, the difference in these energies of our resulting molecular orbitals is such that we create what's known as a bonding molecular orbital. So a bonding orbital. So this is from our additive. So this contains what we call now bonding electrons. And then the subtractive interference, or the destructive interference, this creates what's known as an anti-bonding molecular orbital. Now, just because it's anti-bonding doesn't mean that it contains no electrons. It's an anti-bonding orbital because it is the anti or subtractive combination of our s orbitals. And you'll notice it's almost the exact inverse of this. So this was like a straight-on, head-on, smash these orbitals together. This almost looks like take our orbitals and do the inverse of smashing, pull them away. So we say the antibonding orbitals contain antibonding electrons. And we indicate antibonding electrons or antibonding orbitals with this little asterisk. Okay, so we have these head-on combinations of our s orbitals that could combine in two different ways. The first is our constructive way, which results in our bonding molecular orbital, or our sigma s orbital. And then we have our destructive or subtractive interaction, which creates our anti-bonding molecular orbital. So this is the formation of these sigma s molecular orbitals. So we have the sigma s and sigma s star bonding and anti-bonding MOs. And this is what they look like. However, those are not the only orbitals, those s orbitals, that can undergo a head-on combination to form sigma molecular orbitals. So let's look at the formation of what we call our sigma p molecular orbitals. And just like we said that sigma s MOs result from head-on combinations of s orbitals, very similarly, sigma p molecular orbitals result from head-on linear combinations of p orbitals. So based on how I've drawn our p orbitals so far, I have used this Cartesian coordinate system where y is up, x is left, right, and z is out. So for us, the p orbitals that are aligned such that they can combine head to head would be our px. This is like px coming together with px. Okay. So here we have our linear combinations of our p orbitals. So up top here, this is our constructive or our additive MO. So we have this head-on combination that results in an additive new MO, which is called the sigma px bonding molecular orbital, and it is the px because these guys that are starting out here, they are oriented along the px axis. This is why we call this the sigma px bond or bonding MO. And then down here is showing our destructive combination. And another way to think of this is we've got these px orbitals, and instead of looking at the addition of the inverse, I could show this as the subtraction of my normal. And here, I want to make this match what we see up here. So if I've got red and then blue and blue, the difference between these, or the anti-combination, or the destructive combination, which is that difference here, the subtraction, is also what is represented up here. So notice we've got red, blue, instead of red facing red here. This is why they're treating this like a plus in this image. So it is still a head-on combination. It's just a destructive combination or an anti-combination forming our anti-bonding sigma pxmo. So you'll notice that just like in our sigma s antibonding, we have this region here between our nuclei where we have no orbital density, so we call this a node. We also have a node here, resulting from our sigma px formation, px star. And this is the primary means that atoms have in molecular orbital theory of forming single bonds. So they can form sigma SMOs or sigma PMOs, where this is our resulting molecular orbitals here from our initial atomic orbitals, our px orbitals. Okay, in our next video, we're going to look at how we can make these pi orbitals, or the potential for double and triple bond formation. So we're going to look at what happens to our p orbitals that are not combining in a head-on manner. So we're going to look at the px and the pz, the py and the pz orbitals.